Okay, this is 110 Acoustics. We are recording our second Zoom session for the year, for this semester. That little white bar at the top is probably just at the edge of my cupboard where my computer's sitting here. Yeah, we are recording and we are in Unit 1. We're talking about frequency, wavelength, and speed of sound. If I share screen, well, let's see. Share screen. And I make this smaller. Oh, you'll see some weird picture of Iceland on my computer screen over here. Isn't that weird mountain? Kind of a strange looking thing with a couple of Iceland ponies or whatever. Anyway, in our notes last week, we moved on down. We talked about sound, basically what the heck it was. And we talked about the waves, the motions of molecules in air. We talked about condensation and rarefacted right here, this highlighted stuff here. And we said we drew those like waves because it was easier. So if I go to my PowerPoints here, we drew them much like this picture. You can see the squeezing and separating of molecules made by a tuning fork. And this picture showing you another similar thing, series of squeezing and separation of molecules. This way, picture showing you the same thing, squeezing and separating of molecules. If a tree falls in the woods and nobody's there to hear it, is there a sound? Well, did this stuff occur? If this stuff occurred, there was sound. Okay, so sound is a series of squeezing and separating of molecules. Otherwise, if no sound is occurring, there is no such pattern as you can see on the screen. You've just got random general Brownian motion. Just move, they call that Brownian motion, as is seen in your notes as well. So if you go in your notes, you'll see that as well. Brownian motion, random movement of molecules in air with no sound. But once the sound occurs, you've got that sudden pattern. And the squeezing together is called condensation, and the spreading apart is called rarefaction. And we draw these like waves. Follow my cursor. We draw them like waves simply because it's easier to do that on a piece of paper. Okay? It's easier drawing this than it is drawing this. So if I stop sharing for a second, sound waves don't go up and down, because if they really did, you'd be going like this, listening with your head, okay? So sound waves don't. They radiate out from a center that's creating the sound, and they're a series of squeezing and separating of molecules. Quite simply put there. So, back to sharing screen and looking at our PowerPoint slides, we can see here, well, we have another person here. Okay, great. You can see here a speaker making the sound. Okay, the speaker here is making the sound. And you can see here it's white, and then it's black, and then it's white, and then it's black. And that's the white would be the rarefaction, the bottom part. The black would be the top. The white would be the bottom, the black would be the top, and then you can look at this speaker. It's making a different sound. Notice that the white and black are tighter together. They're shorter. This one begins with a condensation, and then a rarefaction, and a condensation, and then a rarefaction. So you can see there's more black and white stripes here than there are here. This means that this sound wave has more bumps. The up is always the condensation, the down is always the rarefaction. So this sound would be said to be a higher frequency. There's more bumps over time. And with sound, the time unit is always a second. So how many bumps per second? How many squeezings per second would be the frequency of the sound? We said a sound wave also has 360 degrees, just like a circle. 0 degrees, 90 degrees, 180, you know, or here, going all the way around, and now you're back to 360 again. Same with the sound wave. 0, 90, 180, 270, back to 360. Now you're back where you started. You have one condensation, one rarefaction in that particular picture. Same here. And you can also look at sound waves in terms of phase. Yeah, 0 degrees phase, 90 degrees phase, 180, 270, 360, and you're back where you started. Here's another sound wave. Same frequency as this wave. Same, it just started with a rarefaction and has a condensation here. Otherwise, there's no difference. Same with this wave. It's got one cycle is shown as well. See, there's one cycle shown, one complete rarefaction, one condensation. Here, one condensation, one complete rarefaction. As soon as you have a pair of those, as soon as you have a pair of them, a black and a white, that's called a cycle. So how many cycles per second? And we said in our notes that we've abbreviated that as frequency. So remember this little section here, sound longitudinal versus transverse, okay? And that just means the sound waves are shown like this would be a longitudinal waves. These are transverse waves. We draw sound waves like water waves, but really they aren't. Really, the squeezing and separating is happening on the same plane as the direction the sound is moving in. Whereas water waves, as is shown here on the right, the wave may be moving this way, but the up and down motion is going up and down. So the up and down is perpendicular to the direction of the wave, like water waves. So we draw sounds like transverse water waves, but in reality, they are longitudinal waves. The squeezing and separating is happening on the same plane as the direction of the movement of the wave. Okay, now you can see these three particular waves over here. The top pair, the middle pair, the bottom pair, and the top pair have the same height, so they have the same amplitude. The middle pair, but they're different in frequency. One of them has 4 bumps and the other one's only got 2. And over here, these waves are the same in amplitude, same in height. There's the same number of bumps. They're just slightly out of phase with each other. And in this bottom pair, you have the same frequency, the same phase, but they're different amplitudes. So you can see that sound takes place over 3 dimensions: frequency, amplitude, time. Same here. This slide's showing you the same thing. A top pair of waves that's different in amplitude, but same in frequency and phase. The middle pair, same in amplitude, same in phase, but different in frequency. The bottom pair, same amplitude, same intensity, different phase. So now we get to where we got to the end last week. Now we just did a little bit of a review, and now we are where we got to last week. Now I look at this picture carefully. There's 2 things being shown here. The top one is showing period. The bottom one is showing wavelength. Okay? So period is the time it took for one cycle to occur. Look at this. Follow my cursor. The time that it took for that to occur. How many bumps per second? Well, there's 1 cycle, 2 cycles, 3 cycles, 4 cycles. So if this time length was 1 second, you had 4 cycles per second. So how long did it take for 1 cycle to occur? 1/4 of a second, because you had 4 cycles in 1 second. So you can see that the word period means the time it took for 1 cycle to occur. So we call frequency in this field hertz, capital H, small z, hertz. That means cycles. So how many cycles per second? What's the hertz? This would be, the top one would be 4 hertz, because you had 4 cycles in 1 second. So what was the period? 1/4 of a second. Well, 1/4 of a second for 1 cycle to occur, because you had 4 cycles in 1 second. So period is always the inverse of frequency. In other words, frequency equals 1 over period. Okay? Frequency, hertz, equals 1 divided by the period. So if you took the period, if you said the period was 1/4 of a second, 1 divided by 0.25, because 0.25 is a quarter of 100, you know, you'd get 4. So you're, and the same, now look at the bottom. You got wavelength here. Here, you're looking at the physical length of the wave. How long is it in feet or inches? So these are the 2 things we're covering today, period and wavelength. We'll start with period. So let's go to our notes so we can look at that more carefully. Scroll down, and I told you last week, don't worry about this stuff. Except you're often going to see sound waves described as sine waves. You'll sometimes see them as referred to as sinusoidal. That comes from the word sinus. Your sinuses behind your nose. Sinus is the Latin word for bend, for bends. And sound waves, of course, go up, are shown as up and down. So that's why they call them sinusoids. Anyway, here we go. Don't even worry so much right now about 2 ways to represent sound, although we talked a little bit about that last week. Waveform is what we're talking about today. Sound waves, okay? The vertical axis, the horizontal axis is time. The vertical axis is amplitude, okay? And spectrum is another way of showing sounds, but we'll talk about that later. Here's the picture here, this section right here, okay, dealt with these slides that I showed you right here. This one and this one. These, whoops, not this slide and this slide deal with this particular section. Those are the 3 dimensions of sound. It takes place with amplitude, frequency, and phase. Now looky here. Pure tone. That's a simple sound, a single sine wave. All of what we've been showing you are simple sounds. These are simple sounds. That's one frequency. Here's another frequency. Here's another frequency. Here's another one, and another one, and another one. Most sound waves, it says in your notes, are actually complex, meaning there are a bunch of frequencies together. Even when I'm talking, my voice has a bunch of different tones together. Same with Alyssa Lloyd's. Hers would have a different ones. Same with Ms. Lynn Royers. Everyone's voice is different. Noises are different. Traffic, door slams, talking, yakety yak, all music is hundreds of frequencies together. So that's what we'll be talking in a few weeks, is about complex sounds. But for now, let's stick to pure tones, because actually pure tones is how we test hearing. You're going to wear a set of headphones and you're putting pure tones into the person's ear, and you're measuring how loud you needed to make each of those pure tones for the person to hear. You'll be checking tones around middle C in music, and high C, and octaves going higher, and then you'll test bass tones. You're going to check how a person hears treble and bass. Okay, and then you'll talk about the degree of hearing loss someone has, because you tested his or her hearing under headphones, and what was the stimulus you used? Pure tones. So let's talk about pure tones here. Now we are at frequency and period. So here's the section. It describes in notes what we've been talking about. Frequency, highlight it right there. The number of times something happens per some unit of time. Your footsteps. How many footsteps per second? What was the frequency of your footsteps? Okay, if you're running, a higher frequency, more footsteps per second than when you're walking. For sound, frequency refers to the number of cycles per second. And hertz, 1 hertz is 1 cycle per second. A sound with 100 cycles per second is 100 hertz. Period is the time it takes to complete 1 cycle. So if a sound is 1 hertz, then its period is 1 second. But if a sound is 100 hertz, then its period is 1/100th of a second. Because if 100 cycles took place in a second, the time it took to complete 1 cycle was 1/100th of a second. Therefore, that's why we say frequency and period are inversely related. As frequency is increased, period is decreased, and vice versa. So the formula to remember and put a star by this. Frequency equals 1 divided by period, or period equals 1 divided by frequency. They are inversely related. This is the first formula you must memorize, okay? This is a formula that will be asked on quizzes. It will be asked on midterms. You will be asked to calculate what's the frequency. If the period is this, what's the frequency? And if the period is x, you'll do 1 divided by x, and you'll get the frequency. If I say what's the period, and I'll say the frequency is 200. What's the period? If the frequency is 200 hertz, you'll do 1 divided by 200 with your calculator, and whatever you get, that's the period. Okay? Now, humans can hear from as low as 20 cycles per second, or 20 hertz, all the way up to 20,000 hertz. It's different for whales, it's different for dolphins, it's different for dogs and cats. But we humans, that's our frequency range of hearing. And within that range, our very best hearing is between 1,000 and 4,000 hertz. Those frequencies right there, those are the sweet spot of our hearing. Okay? So those are the sweet spot of our hearing. That's where, in speech, that's where the consonants are. The sounds like sh, t, k, p, t, all the lip sounds, the high-pitched. Okay, is the word church. Okay, say the name Saul, Paul, call. See how all those words have ah. Think of these words that all rhyme. Hat, fat, sat, bat, cat. The ah is a vowel, and ah comes from your throat, and ah is low-pitched. Okay, doesn't fall in that range of 1,000 to 4,000. The sounds that do are the consonants. So if I say hat, fat, bat, sat, cat, they all have ah, but what makes them different is hat, fat, bat, sat, cat. Those sounds, the sounds that make those words different, are the consonants. The sh. When you can't hear those, your complaint is, I can hear young people talking, but they mumble a lot. Now, that's exactly what elderly people get. They lose high-pitch hearing, and they lose the ability to hear between 1 and 4,000 hertz. When you've lost those frequencies, you can hear, but you can't hear what they said. Did they say kittens or mittens? Did they say dishes or fishes? Okay? It's that kind of a thing. And that's what you're going to be dealing with as hearing instrument specialists. Most hearing aids provide emphasis for those frequencies because those are the frequencies of most hearing loss. So we'll keep trying to tie acoustics with what you're going to do in reality here. All right. So let's share screen again. Share screen, and look what we've got at the bottom here. So now you have period. We've got that. That's always, whenever you think of the word period, always look at your wristwatch. It's the time it took to complete one cycle. The time, okay? Now we're looking at wavelength. Wavelength is the physical length of the wave. In other words, if we go to our PowerPoint slide and look at a particular picture here, how long is this guy in inches or feet? How long are these? How big is it? Is this 4 inches long? Is this 4 inches long? Is this 4 feet long? Is this 4 feet long? Now, before we do anything else, I'll stop sharing and I'll just emphasize here. Okay, I'll just emphasize that in science, most people don't do inches and feet. Okay, in science, most people use metric. In fact, people all around the world use metric in science. in the USA, Canada, England, Holland, Europe, no matter where you go. But most people in the United States talk about things in miles and feet and in inches. Okay? In Canada, we're a little bit more British than you guys are. Okay? We're a little bit different than that. In Canada, we use centimeters. In Canada, we use kilometers. In fact, every country uses kilometers for distance except USA and England. Other than the USA and England, all around the world, no one uses miles. That went out with the dodo bird. In Canada, we still talk about feet and inches a bit, but we also talk about centimeters and meters. Now, how long are these guys? Because we need to know this because we're taking science. And as I said, even in the US, in science, they use metric. So how big is a centimeter? It's as big as your fingernail. That's the length of a centimeter. Okay? How big is an inch? About 2.5 centimeters. Just something to remember. How big is a meter? A meter is about a yard. A yard is 36 inches. A meter is about 39 inches. So pretty close, a meter. So a centimeter, C-E-N-T, is 1/100th of a meter. Cent. Just like 1 penny, 1 cent is 1/100th of a dollar. The word cent comes from France, cent. It just means 100. Okay, so a centimeter is 100th of a meter. A kilometer, kilo, means 1,000. A kilometer is 1,000 meters. Everything's based on 10 in metric. Freezing in metric is 0. 100 in metric is boiling. A little easier to remember than 32 and 212. Okay, it's a little bit easier. Everything in metric is based on 10. But I just thought I'd just digress and tell you that. Now let's look at wavelength. You can calculate wavelength in terms of feet, inches, or in metric. So we'll just look at it. Wavelength versus frequency. Just like period, wavelength is inversely related to frequency. Just like wavelength, okay? Just like period. As the frequency goes up, the wavelength gets shorter. Let's look at the picture in PowerPoint that helps to describe that. So let's go to PowerPoint here. This slide right here. I'll make it bigger. There. This is a lower frequency than this one. This one's got fewer bumps per second than this one. Okay? So the wavelength, one wavelength is one cycle. Yep, that's one wavelength. That wavelength is shorter than. So the period got shorter as the frequency went up. The period, the time, if this is time, look at I'm circling here. This is 1 second. The time it took to complete one cycle is shorter here than it is here. But also the wavelength is shorter here than it is here. So both period and wavelength are inversely related to frequency. Here, look at the wavelength. 1 condensation, 1 rarefaction. That's shorter than here, 1 rarefaction and 1 condensation. This is way longer than this. So that's the point that I'm trying to make here. So when we look at our notes, wavelength also involves the speed, or wavelength involves the speed of sound. So how fast is sound? Sound goes 343 meters per second. See that right here? Now, you want to put that in miles an hour? We can. In fact, why don't we just go to the next page and do that, and we'll come back here. Let's just talk about how fast sound goes. Speed of sound. At room temperature, sound speed is about 340 meters per second, or 1,130 feet per second, or 1,238 kilometers an hour, or 766 miles an hour. Okay? So we're giving it to you in both. You don't have to sit there memorizing it, but I would memorize the 343, or I would memorize this one here. okay? Because we usually talk about second, how many per second in sound. We don't usually talk about the speed of sound in miles an hour. But when you're looking at miles an hour, that kind of puts things together for me. Because how fast does a 747 jet fly? How fast do airplanes fly? They go about 600 miles an hour at top speed. So the speed of sound is a little bit faster than a jet. Okay, a bit faster. So when you're flying from St. Louis to Kansas City, you're going about 500 to 600 miles an hour. It'll take you about probably, I don't know, I think Missouri is, but it'll take you a little bit less than an hour, I think, to fly from one place to the other. Okay? But in terms of per second, it's 1,130 feet per second or 340 meters per second. So now let's move up to back to where we were and let's figure out wavelength. Here we go. Wavelength involves the speed of sound. Wavelength is equal speed of sound divided by frequency, or you can say frequency is the speed of sound divided by wavelength, or you could say speed of sound equals frequency times wavelength. And all I'm doing, it's just like saying this, 5 is equal to 10 divided by 2, or you could say 2 is equal to 10 divided by 5, or you could say 10 is equal to 2 times 5. They all make sense. All we're doing is flipping the numbers around, aren't we? Okay? We won't be using this one much. That one we won't be. But these two, we will be. And those two, I would memorize. Just like you did with frequency is 1 over period, period is 1 over frequency. This is your second set of formulas to memorize. Just have them down, okay? Not just while I'm talking here, not just during this Zoom session, but make sure you've got those puppies memorized after, so that when you get a quiz, you don't blank out and go, oh yeah, I kind of know. You got them down. Okay, so, and the trick to remember these two things that I've highlighted here is that speed of sound is always on the top. Okay, speed of sound divided by frequency, or speed of sound divided by wavelength. So here you go. Formula. Wavelength. Sometimes in Latin they call it lambda or whatever. Don't worry about it. Or Greek. Wavelength is speed of sound divided by frequency. There you go. So, for 100 hertz, how long is a 100 hertz sound? How long is that? Well, wavelength equals 340 divided by 100. And you divide that and you'll get 3.43 meters. 3.43 meters. 3.5 yards in length. Whoa, look at this one here. In feet, let's calculate the same thing. Wavelength over 1 is equal to 1,130 divided by 100. And you do that, and you end up with 11.3 feet. So same thing, 11.3 feet is the same thing as 3.43 meters. Same thing. One's in metric, one's not. Here, 250 hertz. 340 divided by 250 equals 1.37 meters. Or 1,130 feet divided by 250 equals about 4.5 feet. 8,000 hertz. Ooh, that's a really high frequency. 343 meters per second divided by 8,000, 0.04 meters. Or if you did it in feet, 1,130 feet per second divided by 8,000, what is that? 0.14 feet. Okay? So always remember, when you're doing the calculation, always say what it is. Don't just say 1 point or 0.14. Tell me what it is. 1.14 what? Inches, feet, miles, okay? And same with this one. So here we go. Same with the top one. If it's in metric, and if you get 340 divided by 250, if you end up with the number 1.37, 1.37 what? Meters. Okay, because you calculated it in meters here. You calculated it in meters here. So you said what it was. Here's an important concept for people who fit hearing aids. Low frequency sounds bend, highs bounce. Let me stop sharing, and so I can really emphasize this. Little short sound waves, high frequency, treble sounds, crickets, birds chirping, the letter S, high-pitched sounds, okay? They are short, of course, because they're high frequency, and those little sounds don't bend around things very much. They bounce off of things. Ding, 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 ding. They bounce off your head. They bounce off the walls. Low frequency sounds, bass, elephants, low pitch sounds. Those bend around things. They bend around things. So elephants, let's look at the animal kingdom. Elephants emit, they got big ears, they emit low frequency sounds below 20 hertz, sounds we can't hear. Okay, and those low frequency sounds bend around rocks and trees over the hill and down into the next valley below. That's how elephants can track each other's movements. Zoologists from airplanes would be amazed and mystified how trains of elephants would be walking in perfect parallel like this. And they'd be far apart, miles apart. But it's because low frequencies bend over the rocks and trees and over into the valley below, the next valley over. Highs don't. So let's look at an animal that uses high pitches. Bats. Bats can't see. They're blind. They fly at night. They catch bugs. How do they catch bugs if they can't see? They emit high frequency sounds way above what we can hear. And those high sounds are so short, and they bounce off the bugs, and they bounce back, and the bat with its big ears can hear exactly where the bug is because it's using high-pitched sounds like radar, and it's catching the bugs. It can eat the bugs at night, okay? So highs bend, or highs bounce, I should say, lows bend. Now, in hearing aids, this makes a difference, okay? In hearing aids, high-pitched sounds coming out of the hearing aid into the person's ear can easily bounce off the person's eardrum. They can leak out past the hearing aid and get picked up by the microphone of the hearing aid. And then the hearing aid amplifies the sound, and it goes and bounces off the eardrum again, bounces back out, the mic of the hearing aid picks it up, amplifies it, spits it out against the eardrum. You're getting a vicious circle. It's called feedback. It's the high-pitched whistle coming out of a hearing aid. Okay? Just like when you're talking in a mic and you're in a room and you go too close to the speaker. So now not only your voice is coming into the mic, but also sound from the speaker is coming into the mic. And when that happens, you've got that vicious cycle happening again. And then you're going to get that ee. Okay? So feedback is caused by high frequency sounds that bounce off your eardrum and leak out past the hearing aid and get picked up by the hearing aid, and they're amplified again, and you've got that vicious circle. Has everything to do with lows bending and highs bouncing. So these are the physics of sound that are required by the HIS, hearing instrument specialist, to know kind of what's going on. So, and if you're going to be fitting hearing aids, we have to know what hearing aids do and what are they doing. They're amplifying sound, and if they're amplifying sound, we have to have a grip on what sound is. So hence the course, acoustics. Okay, so now let's check it out here. We will, let's see. I want to share screen here. Oops, I want to do that. Okay. I just want to be able to share screen. I just want to make sure that I am still sharing screen here. Okay, I don't know why I keep getting this all the time, but okay, every once in a while I get lost in this, so bear with me. Here we go. Okay, share screen. There we go. Back to our notes and back to the notes. Beauty. All right. So let's just take a look at speed of sound. Speed of sound. At room temperature, speed of sound is about 340 meters per second or 1,130 feet per second. Memorize that. So you got three things to memorize here. Up here, period and frequency, right there. And the next thing is wavelength and frequency. And it's these two guys right here. And it's when you're going to be doing these types here, you need to know what this is in metric or this is in feet. Okay, so there you have it. Now look at this. Speed of light, not sound, light, is 100 million times faster than the speed of sound. Remember we said last week light can travel through outer space? Sound can't. Sound needs a medium. Sound needs either air or water or metal. Sound has to travel through something. If there's nothing to travel through, sound can't travel. So if you and I were standing on the moon has no air. So we could yell till the cows come home and we're not going to hear each other. Okay, sound waves need something called a medium through which to travel. Light doesn't. Now light travels, look at this, 300 million kilometers a second. What, miles an hour or miles per second? Light travels 186,000 miles per second. 186,000 miles per second. Imagine that. Hey, did you see the lunar eclipse last couple nights ago? The moon was red. Do you know how long it takes for light to come from the moon to Earth? I'll stop sharing for a second. It takes the light to come from the moon to the Earth about 3 seconds. You know how long it takes for light to travel from the sun to the Earth? About 8 minutes. Do you know how long it takes light to travel from the nearest star to the Earth other than the sun? 4 years. So if you were going to go on a spaceship and fly to the nearest star that's not our sun, it would take you 4 years to get there and 4 years to get back. You'd be gone for 8 years. It just shows how far away those stupid things are. Okay? So space is huge, monstrous. So we'll share a screen here again, comparing the speed of sound to the speed of light. Well, light is fast. You see the lightning way before you hear the thunder. Okay, so thunder happens way later because sound goes slower. So the speed of sound is 4 times faster in water than it is in air. And it's 14 times faster in metal than it is in air. That's why if you really want to hear a train coming quickly, put your ear to the railroad track. You'll hear the train coming through the railroad track way faster than you will standing by the railroad track, cupping your ears trying to hear the train. Okay? So sound goes 14 times faster through metal and 4 times faster through water. So if you click a pair of rocks underwater and your head is underwater, the sound is traveling from the clicking of those rocks to your ears 4 times faster through the water. So dolphins communicating with each other underwater, sound travels faster that way. Now here's something to remember too. This is one of the thickets of physics. And I'll just say FNO, freak not out. Okay, it's okay. But let's just kind of look at this for a second. This is kind of takes a bit of a mental gymnastics here. The speed of sound depends on the density, that means the mass, and the elasticity, that means the stiffness of the medium through which it travels. Look what I've got highlighted there. Now, elasticity, don't think about elastic bands. Think about exactly the opposite. In physics, the word elasticity means stiff. Okay? In physics, the word density means the mass, like the weight. How is it? Think of a train locomotive. That's got a lot of mass. Think of elasticity. Think of a very stiff spring. So sound, the speed of sound depends on the density and the elasticity of the medium through which it travels. Now, the speed of sound is inversely, oh, don't even worry about that. Inversely related to the square root of density, directly related to the square root of the elasticity. Yikes. Don't worry about that. Just leave it. Air temperature increases, speed of sound goes faster. Speed of sound goes a little bit faster when it's hot than it does when it's really cold, because the air molecules are a little bit more spread out and the medium becomes a little bit less dense when it's hot. So the more dense something is, write this down in your notes. Just scrawl this down somewhere in the margins. The more dense, the more mass something has, the slower sound will go. I'll say that again. The more dense, the more mass something is, the slower sound goes. The more stiff something is, the faster sound will go. And I'll repeat, the more stiffness of the medium, the faster sound will go. So now you got those two things written down. Then you have to say, well, why then does sound go faster through steel? Because steel is way more dense than air. Yeah, that's true. But steel is also way more stiff than air. And the stiffness of steel outweighs its greater density. Okay? That's why sound goes faster through a railroad track than it does through air. True, a railroad track is more dense than air. Obviously, I can move my hand. Here, I'll stop sharing. I can move my hand through air, but I can't move my hand through my hand. This is made of flesh and bone. That's more dense than air. Okay? But why then does sound go faster through steel, metal, than it does through air? Because steel also is more stiff than air. I mean, you can't bend steel, okay? Air, you can just move your hand. So the greater stiffness of steel outweighs its greater density by far. So I'll share screen here and back to our notes. Okay? Share screen. Back to the notes, and we read. Fluids and metals are more dense than air, so why does sound go faster through these media? Steel is 6,000 times more dense than air. But steel is also much more elastic, stiff. The ability to think of elasticity is the ability to resist being bent or deformed. And the elasticity of steel is 1,230,000 times greater than the elasticity of air. So the greater elasticity of steel far outweighs its greater density. Okay, enough on that. Let's go. We're just about done today's topic. Remember, in any medium, air, water, etc., wavelength and speed of sound are all interrelated. And here's something else to put a star by, because I promise this is going to be asked. Speed of sound has no relation to frequency. In air, high frequencies travel the same speed as low frequencies. In water, low frequencies and high frequencies travel the same speed. In metal, low and high frequencies all travel the same speed. They all travel faster, but never think that highs travel faster than lows in air, because they don't. All sounds travel faster in water than they do in air, but in water, all frequencies travel the same speed. And in air, all frequencies travel the same speed. Here's something kind of weird. We'll just describe this a little bit today, just for fun. The Doppler effect and the sonic boom, just for fun. Have you ever listened to an ambulance or a cop car coming toward you? It kind of goes, the siren, and then as it passes you, even a race car. How come the speed of sound goes higher as the object approaches you, and as soon as the object passes you, it goes lower. The pitch of the sound goes lower. The Doppler effect. Sound travels 340 meters per second, or 1,130 feet per second. Well, when the car's coming toward you, you've got the speed of sound plus the car coming toward you. So the speed of sound is faster, and the wavelength got shorter because the waves got bunched together. Because the car is pushing the sound waves. The sound travels 1,130 feet per second normally, but now you've got the car coming toward you as well. So you've got 1,130 feet per second plus the speed of the car. So the sound waves are squeezed between you and the car, so they're shorter, so the frequency goes up. And as soon as the car passes you, sound's going 1,130 feet per second, but the car is going away from you. So the wavelengths become elongated. The distance from the car to you is increased. And so the waves get longer. And that's why the frequency goes down. Cool, huh? And it's the same thing as going above the speed of sound, breaking the sound barrier. Check this out. We'll go to this slide here and go all the way to the end slide here. Well, not quite that one. Let's see if I can find a good slide here. First of all, I want to make sure that I'm sharing screen. Okay, always make sure you're sharing screen. See if I've got the Doppler effect here. Kind of cool. Oh yeah, here it is. Up. There you go. Breaking the sound barrier. When you're breaking the sound barrier, something else is happening. You're catching up to the speed of sound. You're bunching the sound waves all together. So sound's traveling 1,130 feet per second, and it's coming toward you, but the jet is catching up to the speed of sound that it's making. So all the sound waves that are occurring that come from the jet, they're coming toward you, but the jet is also reaching the speed of sound itself. So all the waves are bunched together because the jet is matching the speed of sound. The speed of sound is moving away from the jet, but the jet is catching up to all those molecules that are moving away. All the bunching and separations that are moving away are traveling 1,130 feet per second, and the jet is squeezing them all together because it's catching up. So it squeezes them all into one big condensation, and when the jet punctures the sound, that barrier, all of a sudden you've got a big vacuum behind, and all of a sudden the molecules fill that vacuum, and that's the sonic boom that a jet makes. So when a jet is matching the sound, the speed of sound, it's catching up to the speed of sound that's moving away, and the jet is catching up to it. It squeezes, all the waves are squeezed now together, because they got no other place to go. The speed of sound is going as fast as it can in air, and the jet has caught up to it. So all the waves are bunched together into one big condensation, and there's a vacuum behind the jet, and once the jet punctures through that sound wave that's all bunched together, that sound wave fills in the vacuum of molecules behind it, and that's the sonic boom. You want to know a small sonic boom? The snap of a towel in a locker room. You ever been snapped by a towel when someone does this and okay, you know why that hurts so bad? Because the tip of the towel has broken the sound barrier. Okay, that's why a whip goes that is the sound barrier. The tip of the whip has snapped, and it's broken the sound barrier. It's traveled faster than 766 miles an hour, or it's traveled faster than 1,130 feet per second. It's broken the sound barrier. Weird, huh? So, next week, what we've done today, we've shared notes, we've done this stuff, we'll look at our notes, we've gone to the bottom of Doppler effect and sonic boom. I won't be asking this stuff on quizzes or exams, the Doppler effect and sonic boom. Those are just there for your interest. But the other stuff, Make sure you do know that way. Okay, those two formulas we went over, etc., etc. Next week, we'll talk more about sound fields, reflections, echoes, reverberation. We'll talk about anechoic rooms. What are sound-treated rooms where hearing testing is done? We'll talk about something called impedance, and we'll also talk and finish more regarding resonance, the favorite vibrating frequencies of objects. Okay, just like a wine glass at Christmas. I'll stop sharing here. Like a wine glass at Christmas. You lick the rim, or like a pop bottle when you blow in the top. You've hit the resonance. And all objects have a resonance. Even your ears have a resonance. Guess what your ears resonate with? They resonate with sounds between 1,000 and 4,000 cycles. Remember we called that the sweet spot of hearing, our best hearing? Remember we said our total range of hearing is between 20 hertz and 20,000 hertz? Well, within that range, the sweet spot is 1,000 to 4,000 hertz. And you know why that's our sweet spot? Our best hearing is for that, is because of the resonance of this shape, the resonance of the ear. So you can see that the ear is literally made for speech. Because what lies between 1 and 4,000 hertz? The high frequency consonants of speech, the letters S, F, CH, SH, K, P, okay? The sounds that tell you what the word was. Not that the word was spoken, but what the word was. Hat, or bat, or sat, or cat, or mat, or fat, okay? And our ear is literally made for speech. So I just thought I'd tell you that. Okay, I think we're good to go. This has been our Zoom session for acoustics, our second Zoom session on Unit 1. Next week, we'll complete this unit. We'll finish it with the discussion of resonance. We'll finish it with a little bit about speech and stuff and things and stuff. It's been a slice. Live long and prosper. We'll see when we look at you. All right? I'll stop recording now.